reason why they are not here? No? They were coming religiously all the days when there are classes. So, whereas thought today, no classes, right? On Saturdays, there will be no people. But, and we only need 2 hours. We are not, we don't have anything in the afternoon today. Holy is coming. Yeah, when is Holy? 14. But that's next week now. They leave, but how about classes? Because, yeah, I thought it was 14 Friday, but that's right. It's not this week. As Sir said, there may be more students today. It looks like not having. So in the meantime, let me ask you any questions. And one thing I would mention also when everybody's here, but the MATLAB code, I know yesterday he was asking a question. I mentioned that the code was given maybe to assist. So it's always good that you understand the code before you make changes to it. What I mean is, I know one of the questions was, well, if you change the dimensions, it doesn't work. Yeah, possibly there is something else in the code that is probably causing that, something happening, right? There was an error. So I don't think that I can answer all the questions in the code because this was written by someone and it was done somewhere like 2012, 13, it's more than 13 years ago. So there is no way that we would remember. The only thing was why we gave that code was so you can run it and see the same results or similar results. Then you can break the code down and understand how it's being written, so that when you make changes to it, you learn from it and then you basically update the code the way you want it, right? It's like some questions they were asking was, why is there so many different MATLAB M files? Mainly because everything is split into smaller subroutines. So these are some people's style, the way that people write, right? So the same way, I think it's not possible for all of us to essentially debug someone else's code. It's going to take hours, to go through. That is right. That is right. You will be able to get it, yeah. So that's what he was trying to, I think, finding an easy solution, but that's probably not going to happen. Yeah. So like what you did, you padded and it worked. But that's the way. But I know he was asking, why can't I do it by 6 by 6 or whatever? Yeah, 8 cross you are working like. No, but he has a point. He has a point too. But the thing what I was mentioning was that the MATLAB code, you could do it, like you can make it customized to a particular system, right? That's what normally we do. Right. I think so. I think that's what I would suggest. To answer your question yesterday about that, the dimension, what I was discussing is still, I know there are still a lot of students missing. So in the meantime, I'm just asking, the question you asked, I was just telling them that the MATLAB code was provided to assist, right? So that you see how it was done. But there were so many things that even I don't know because this was written by a student of mine, not our student. And it's been over 14 years. See? So, and I think we provided that as part of the book so that students can, whoever using the book, they can run the code and see, but then they have to go through the math and then fix the, like if you change the system, right, then you basically You might have to change something in that. Remember, you were asking what is that particular variable? Yeah, and those kind of things I think is very hard for us within short time. That's what you were saying. I would encourage you to run it, but then after this you understand like what was how it is written, and then you compare it with the slides in terms of the dimension. Then you see, okay, if I'm changing the dimension of the system, what changes do I need in the code? That's one way. The other way is you can actually draft your own MATLAB. I think that's what I would encourage. Because remember, let's say you are going to a job or anywhere, you have to go from the scratch. Nobody is going to provide you with the code, honestly. So that's always going to be there. Okay? So that's number one. And we'll see today, without recording, I will show you some hardware. Some example of real, like remember I said, autonomous truck or vehicle. And we'll talk about some other things on the optimal control part. Also, on a lab level robot, formation control. So I'll show you some videos. I thought I would bring it in. I know I was originally waiting, but I will also show that the last day. Since we're ahead, I thought, okay, I will come. I used the first half. I didn't know most people don't show up, I thought everybody, the way I understood was everybody's going to be here, especially today you guys don't have classes. So, first half I will finish up that nonlinear control system. And then the second half I thought maybe after the tea, play some videos and so you can see anything I teach, everything is hardware implemented. And unless it's last 2-3 year old stuff that we are developing in the, but everything else is usually implemented, It depends. We have used variety. Like I'll mention that today. So some applications we were 8085, 8086, and some we have gone. We thought we need more powerful processor for neural network. Engine emission control. That's a really nice one. We put on multiple engines without changing the structure of the controller except a small minor changes. There I used. Oh yeah, sure. We have used Raspberry. Yeah. So, but Raspberry Pi is probably more powerful. You'll be surprised. We may not even need that. You see? You think that, you think neural network, remember we talked about 3 neural networks? You may not need 3 neural networks. You'll be surprised. And I'll show you one of those mobile robots. It's an 8086 processor. So, I think sometimes, and then engine we thought, we need a lot, and we did some study, I don't have in the slides, but where we increased the number of neurons and we wanted to see how much time it takes. Hardly it took any time in tuning those things. So there we used, I think, what is that, not Intel based, this other one, not coming, but we used that processor, which is more powerful. It's a 900 megahertz crystal. And we realized that we were not even using 10-15% of the processing. You could, based on the number of multiplications. Remember in the flowchart, you take that's how we do it. You take the flowchart, you know the size of the matrix. See, that's why it is needed. Once you know the MATLAB code, you know the size of multiplications and additions you need. You see, that's all you need. And how many nonlinear operations you need, right? Then what you do is each processor, essentially they'll give you a table. They'll give you a table like how many flops per second, or what is the time it takes to have one addition, one multiple. So you can compute the time. You see? So I think you could definitely. So in the discrete time book, I don't think this book has some, maybe I don't remember, but the discrete time book has a chapter on engine control. The whole chapter with some not MATLAB C code in there as well. But we don't want to put the code because it takes a lot of pages. So We had some code in one of our books in 98, neural network book, but that was in continuous time. Only we give a few lines MATLAB code, But then what happened, we realized the book was getting bulkier and the cost would go up. So we cut all this and then we were using, providing this. That's why the MATLAB code was provided as a way to assist, not to part of that book as well, So, okay. So just wanted to let you know. Any other questions? So do you know why there are not many people today? Because we thought there were more students. Huh? Today is the day. See, faculty are here.
No, they know everything.
Yeah, that's right. So us who have to learn. Right.
We don't know anything.
Anyway, alright, so I'm going to start. I think I brought that laptop just for a few videos. I thought I would just show, but maybe some people will show up at 11 or something.
They will join.
Because yesterday, all right. So, any other questions? So that's why I kind of gives you a heads up. Don't expect that you would understand the code because hardly, we didn't go through it. And you may want to, just like I said, put some commands to display, let's print intermediate stuff in there so that you understand what is being done in that part of the code. And in the same way, those subroutines that were separated out. And Sar went through a few, right? Remember, he was going through. But the tutorials, then it will eat away. It won't have, you won't be able to go beyond one program. And second, we really don't want to teach MATLAB code. That's not the goal, essentially. You see? So that's the main reason, okay? Any other questions? And anything we covered? So you guys are continuing to spend time working. At least what I suggest is you run the MATLAB code as it is. See if it matches or close enough with the results that we were talking about. Understand that first. Then you go into the MATLAB code and see how or where these are coming out, How is it done? Then you understand that, okay, for that problem, this is how it's done. The dimensions are this, and then you can go back and adjust whatever you want to do, Okay? All right. So I think we are lecture number 8. So we are one lecture ahead. I think that's what I wanted to let you know. So in the last class, if you remember, mainly we are talking about these delays in packet losses. So in this chapter, we won't deal with quantizer. But you can have a quantizer, right? You can do a quantizer also. But here, what we are only dealing with is a nonlinear system, and we are only dealing with delays in packet losses. Yeah. Okay. So and then you have the controller to the actuator delay. So remember, we made some assumption that these are independent because that shows that the reason why is it independent is because if there is a delay congestion, we really don't want to see that happening here in this side also. And that's why we assume that these two are, the network is wide area, enough bandwidth so that it doesn't influence something happening here, doesn't influence on this side. Okay? And then we don't also have this quantization. Okay? So this is what a network control system, this is a nonlinear. So we are getting into nonlinear, we have to use neural networks. and again, like what we talked about it, you start here, it takes some time to reach the controller. And then from the controller, you compute something, and then it takes some time to reach the actuator. So we call that as a kind of a close to round trip time. This time total time it takes. This is the round trip time. It's not exactly round trip, but it's close to. Okay. So I think you got to think that way. And we also said the other assumption is the sum of network-induced delays and quantization delay is bounded, and initial state is deterministic. So when you are selecting those initial states, we are assuming those are deterministic, right? So I think that has to be clear. And I'll skip this. So what we did, the first step is we took the nonlinear system in continuous time because it's easier to model. We converted that into a discrete time with the packet losses and delays. Very similar process like we did in the linear. Okay? This is a little bit involved, but I want you to look at it and do this. And there are two ways you could do. You could use, if you know the states are measurable, like we talked about it. If the states are measurable, you could construct an argument vector, or you could actually use the output and construct an argument vector. If you're using the output, it's called input-output system. You see that? But it has its own nonlinearity, F and G. If you're using the state, you also have another H and L, nonlinearity. So they're all the same. Only difference is, you see here you're using an input to Z, the state. Here you're using the input YK naught, you're using the output. Otherwise the same. Okay? So this was just to show you that no matter whichever. So then this part is standard. We define the value function. We use the Bellman equation here. You see that this is the Bellman equation. This equation is the Bellman equation, a recursive equation. But we have this, since we have the packet losses and delays, we are using the stochastic domain, expected value. And then basically you do the dynamic programming, right? So last time we went through this part with an identifier. All this we have covered, okay? And then we showed SAR actually gave you some papers. Remember that? The papers essentially give you maybe a little more details in there, okay? So I would encourage you, I normally don't want to put the papers because sometimes it could be more compact, but it looks like there may be more information in the papers, than in the slides. I just made it so that you can finish it off within that 2-hour lecture. Okay? So I think, and I also want you to focus this. You look at that in the proof. Not only you are showing boundedness, you see that here, this cap here, essentially showing that here is my optimal control value. Here is my actual control value. I'm showing that the expected value over time between the difference of this is going to be bounded by a bound du. And du is a small. So what we are trying to prove, this is a finite horizon. What we are trying to prove is the error between that actual control input and the optimal control input is to be very close. Now why is it not exact? Why is it not exact? Why is it not converging to that u star in this case? Why? And don't feel bad, don't feel shy. You can guess, why is it not, they're only showing a bounded. See here also, we also showing here also it's bounded in the mean, but we are not showing asymptotically stable or, we're not showing that UK hat converges to UK star. Why? So what is that causing that bounded result, not asymptotic here? In this equation, for example, look at this equation. What is causing that not asymptotic? We need to talk louder. There's fans running here. So what is that? What is that? You will never be able to show asymptotically stable unless this particular term becomes 0. This is nonlinear update law, but that has nothing to do with update law, nonlinear or linear. But there is a term in the nonlinear case that's causing the error to be bounded rather than converging asymptotically to 0. So if it converges to 0, that means, UK hat goes to UK star, right? The optimum. But here it's reaching close, therefore we are claiming it's bounded in the mean. So what is that? In this equation that's causing, or if you go to the next equation, we go into, let's say, in this equation, for example. So what is that? That term that is making it non-zero.
Taking expected value.
Huh? It's an expected value, but that won't be, but there is some other thing. So what is, in this equation, what is the term that is non-zero? So the first term is what? The first term is basically approximating the bulk of the value function, right? So this is a neural network, output WB weights multiplied by the basis function, right? And what is this term? What is that? So what is that term? So those who know, how many of you know neural networks? A little bit. You know neural network, right? So what is that term? Right, why? That's my question. You will be able to, but what is that term? Usually pops up in neural networks. So the target is there and this is actual. This is a target value, right? W. That W is the target weights. You see? So what is this term called? So who else know? Who else has taken a neural network class? Other than her. Is there anybody else? Probably not. So this term we normally called as an approximation error. So this is the output of the neural network. So a neural network equation. Okay. So let me see my cursor here. Okay. So f of x. So if you are trying to approximate a function using the neural network, is basically the W transpose phi. Okay. Phi of x plus epsilon. So this epsilon is called approximation error or reconstruction error. Okay, approximation error. So the way you can drive that error to 0, if it's a single layer network, you have to have your neurons in a hidden layer, infinite number of neurons. So that means that as you increase the number of neurons, keep going to infinity, that error value keeps decreasing to 0. Is it practical to have infinite neurons? No. So that's why you always have some error in it. You got it? So if it's a multi-layer network, that epsilon value will be smaller than a single layer. But a multi-layer network, you have more variables, like you can increase the number of layers, you can increase the number of neurons per layer. So all that stuff you can do. You see what I'm trying to say? So that epsilon is error. You will not be able to drive that error to 0, but you can make that error as small as you want. So since that error is non-zero, usually in every proof you only show it's bounded in the mean. Don't forget that. Okay?
Any questions here? I know that's a quick entire course in neural networks in about 10 minutes. Okay, a 10-minute explanation of a neural network. It's pretty fast, isn't it? So that's basically what it is, okay? So you always see, that's why we always say that bounded in the mean or boundedness, because always when you use neural networks, you always have some error. It's called reconstruction error because it's trying to approximate the function f of x. Remember in Q-learning you're approximating A and B? They're the same thing. And here you're approximating f and g. Remember the capital F, AZK like we have ZK and whatever. So that's what you're doing. Okay? So I would encourage you, if you're a student, remember I told you, I would encourage you to take a class on neural networks. Don't leave, because these are skill needed. If you go, you'll be outdated. Or you may have to take a PhD, either here or email it to me, if you're interested in a PhD. Remember I said that? Yeah, so I think it's important that you need to have the skill. Things are so changing now. In fact, every curriculum everywhere is being updated. Yeah. And it's not going to be going away. In fact, I have been to other campuses, some other ones in IITs. They do have a course on, they call it either computational intelligence or machine learning course, which basically teaches a little bit on neural network, fuzzy logic, evolutionary computation, something like that to give you the background. Probably like 4th semester or something like that. So I think it's necessary. Remember that. Okay. So this is clear. So we show the mathematically that it's bounded, right? That's what we did. And the same thing here too. We are claiming it's bounded here and we show this is bounded. And that bound is a small, and it depends on so many factors. One is you can increase the number of neurons. You can also essentially to make it smaller. Okay? But it won't be zero. I want you to understand that. It won't be zero. Whereas a linear system you can do is zero. But for nonlinear system you can always have some error. Okay? Any other questions? So this is what we did last class. Flowchart, we went through this example. Okay, I want you to go through this example. And then let's do the nonlinear stuff. Okay, so we talked about the heuristic dynamic programming. This is a method which uses the policy and value iteration. So it's called HDI. And I'm going to look for paper. I asked, I have no access to Google. So I'm asking one of my students to send me one of the papers so I can pass it to you. So this approach called heuristic dynamic programming uses a value iteration, a different approach to solve the same thing. And there are some problems like I mentioned in this approach, but we're going to use this to compare our approach, to compare. This is more like an offline approach. This has got an iteration-based approach, okay? So we're going to compare ours. So now what we're going to do is, so we would now use a different system in terms of the output. So what I'm trying to do is, this is for infinite horizon. So you see that the cost going up to infinity. The other one we did with n minus k. Okay? So that's a finite time. So since we don't know f and g, first step is to use an identifier, right? We talked about it. So we are using an identifier, and you remember that we have a big neural network. So we have one neural network to identify both f and g. And then we define an identification error in terms of the output. This is the estimated value of the output. This is the actual value, your measured value. You are taking the difference. And then you are coming up with an update. And we talked about this. It's very similar to what I presented. And you need the inverse of this matrix. So in order to have the inverse of this matrix, remember we take the history here. And why do you need the history? History, but what condition it has to satisfy? PE condition, don't forget that. What is PE stands for? Persistency of excitation, don't forget that. Persistency of excitation. Okay? That condition essentially ensures that one is by using those history, you are able to see what is in the black box, which is needed for identification. So identification is trying to understand something is in the black box. That's why we call identification. So in order to do that successfully, we have to have that matrix invertible, and the only way we get invertible is that signal has to be input, has to be persistently exciting, and the input signal is here is U bar. You see that U bar here? The U bar signal has to be the input here, U bar. This signal has to be persistently exciting. And that's why you take all the history here, you see that? Okay, there's a meaning with it, there's a reason, there's a meaning to it. Okay, so that's the identifier, because we need the identifier, so we are using one big neural network to do that. Then, just like we did before, we are now using a value function, since we are using the Bellman and adaptive dynamic programming and reinforcement learning. So we are using the same idea that we have been talking over and over again. So we have the approximating a value function. Now look at that. Since we are approximating, there is an error in approximation. You see that? There is an error in approximation. And the same thing, you are approximating the control input. Because in control input, you know the G. You need to know the G, and G is also unknown, right? Remember that. Both F and G are unknown. Just like your Q learning, we did AZK, BZK. Here FZK and GZK. So since that's unknown, we are using another neural network here. If you see here, we are using another neural network. And you see that there is an error in approximation. You see that? So whenever you are using a neural network, you should have an error in approximation. How about the previous example? See this, there is an error in approximation. Of the identifier. Any questions there? Any questions? So you see that whenever I'm using a neural network, there is always going to be an error. Just like we claim that when you are using a processor, there is a round-off error, right? Remember that? The same thing. We have to use this neural network. That error, you cannot make it zero. Theoretically, we can show infinite number of neurons and infinite number of layers, but always there will be a small error. You can make it small, but you may not be able to make it zero.
So one thing, F and G both are linear and non-linear.
That is correct. Okay. Let me go back to that slide. Yeah, it's non-linear. Go ahead.
Sir, why I am just surprised that any properties of that F and G, even though we are not knowing it perfectly, but any properties of F and G is not required. That is not coming. Other than this, you are assuming something error.
Right. I think there are properties that you are required, and not required is, I don't know whether you can find something like that. But I can tell you what is required. One is both this F and G, you see that F and capital G, right? And that's a function of the output, because that's how I'm modeling it in terms of the output. Just to show you, the first half I did the finite horizon, it has a state. The second half, which I'm doing the infinite horizon, I'm doing with respect to output. Just to show you that you asked this question earlier, we could do model it. But once you incorporate the delays and packet losses, that's the equation number 3. Right? So even though you incorporate it in the stochastic domain, it still has to satisfy the Lipschitz continuous property. We have a capital F and G, that is correct. Because that's where, in that transformation only, you are designing the control input. And it has to be controllable and observable. Now remember, we have shown in the chapter 1 that if the original system is controllable and observable.
No, that is okay, but if it is Lipschitz continuous, then there should be some kind of K which should appear.
That's right. That K is that comes in the bound. As a bound. That is correct. So when you do the proof,
That
the
will require at the stability.
stability proof, that is correct.
And that stability proof
Yeah, yeah, yeah.
that should appear.
That's right. It is there. It is there, but I'm not showing all the details, but it's there. It's in the part of the bound that you will get. Because you take the norms, when you are doing the proof, you are bringing in the target weights. That's where you get, and it's bundled into that error, but it should be there. That K has to be there. That Lipschitz constant. Yeah. So that's why I said I can't tell you what is not needed, but I can tell you what is needed.
And this is sufficient.
This is sufficient. That is
Sufficient.
that is.
Sir, I have one question. I am not able to understand. First problem, you are using ZK,
Right.
where state and previous input.
That's right. That's right. That's right. Just to show you that you can design a controller using the measured state, or you could actually transform the system in terms of the output. Let's say your outputs are measured. Then that is the second, that yk0. Remember that?
But when you are using y of k,
Right.
then that u of k minus q r, that is computed based on output information.
That is correct. It's a computer using the output.
But is it possible to stabilize a system only based on output information?
Yeah. As long as it's observable.
Observe.
As long as it's observable, you can do. That's why I said, the professor, when he asked me, I said controllable and observable. So observability has to be there, exactly. So if it's not observable, you may not be able to do it. But if you have that property, observability along with controllability, then you can do with the outputs. Yeah.